Hey everyone. So, is this working okay?
Yeah, it's working. It's just not reflecting.
Okay. Hey live stream. Hope you can hear me all right. But also, hi. Thanks everyone for coming to the workshop here at Least Authority tonight. And we've got Mirco, who's going to be doing the session tonight, the workshop. But I'll just quickly say that Least Authority, well, we care about privacy. We care about security a lot too. We do a lot of consulting within the security space, and then we also do software development too. Not just the really short bit about us. And we're hosting this stuff because we also care about the community, helping to have everybody learn from each other, learn about the latest advancements with security and privacy and software development. And of course, that includes zkSNARKS and Zero Knowledge Proofs. We think that they're pretty cool. Yeah, so we have Mirco here, and this is also being, this workshop is also being sponsored by the electric coin company. Sorry, I keep wanting to call them Zcash, but they've changed their name. And it's the electric coin company, the company behind Zcash. And so yeah, they also are sponsoring this event tonight too. They are users of zkSNARKS too, so they care too. I guess that's what I'll say about us. Now I'll introduce Mirco and probably pass it off to you, unless, did I forget anything? I'm good?
Possibly paperclip for Halo.
Oh, yeah. Yeah, the other thing to note is that Electric Coin Company is also the ones who did Halo. That paper just recently came out. It's a really exciting advancement with zkSNARKS. And they're on board to do a paper club with the Zero Knowledge podcast, right?
Yeah, with one of the authors.
Yeah, with one of the authors of the Halo paper, which to give, I don't know if I need to give the authors credit, but it's Sean Bowe, Dara Hopwood, and Jack Gregg, who are the authors of that paper. So that'll be coming up in the future. Okay, that's it for that kind of business. Now on to Mirco. Mirco, I'm going to let you introduce yourself, because you'll do yourself more justice, and to introduce the workshop too. But yeah, so thanks everyone who's on the live stream, thanks everyone watching the recording, and of course mostly thanks to you all here present and doing the workshop. And thank you to Mirco.
Okay, thanks. I have a microphone.
You're good. Okay. All right, I will get out of the way.
So I'm Mirco. I'm a mathematician, and this is really all there is to say about me. And yeah, thanks everyone for coming, and thanks to Least Authority for hosting and mostly for doing the organization for this talk. This talk is a very basic talk for an introduction to the principle of zkSNARKS. And if it works well, we might have a whole series that leads up to the Halo protocol, which I personally like very much because it is a kind of recursive snark way which might do a lot of good in the blockchain space, especially to solve the bottleneck of transaction verification at some point. Yeah, okay, so one thing I have to note is that this is a workshop, not a talk, so if you don't understand anything, just interrupt me. Bluntly, it doesn't matter, so I want this to be a discussion, and so really just interrupt me. Okay, so what do we do today? I want you to have the major takeaway of this talk, or this workshop, to have some understanding of what zero-knowledge verified computation actually is. And we do this by introducing first an actual 3-bit security cryptographic scheme, which I have developed just for this talk. It's very basic, so we can do all the computation in this scheme. And then I introduce an oversimplified problem, which we use as our running example in the SNARK pipeline. And yeah, and then we just go through it. So the SNARK version we use is the Pinocchio protocol, but this is somewhat similar to all the pairing-based protocols. So usually people use Groth 16 for this, but Pinocchio is somewhat more easy to introduce. So the references in the further readings are, of course, original source here, which is the Pinocchio protocol itself from 2013. And as I said, the optimized version is Groth from 2016. Basically, he made the verifier more effective and more efficient, and the prover kind of too. So another great introduction is this paper that only appeared recently, Why and How zkSNARKS Works, the definite explanation from 2019. I can really recommend to read this paper. This is somewhat orthogonal to my approach here, and it really goes through all the steps. So if you're interested in these things, you should read it. And then, of course, there's a companion paper from me from 2018, which currently is just on Google Drive, so if you want to read it, you can look it there. These slides are not online yet. We will publish them later on, I think. Okay, so let's start with the question, what is verified computing really? Most of us probably know that public key signatures can be seen as short proof of static data, right? So you have a data set, and if you sign it, then you prove the authenticity and the integrity of the static data. But in reality, we don't have just static data, but we also have dynamic computation, right? Things that are dynamic. And so the question is, can we have signatures for computation, really? So that you can prove in the end that you have done a computation properly. So, and if we can do this, can we also hide certain details in the computation, but still get verifiable signatures? And the answer is yes, and of course this is by now I would say well-known standard name. The zkSNARK is one solution to this problem, which means zero knowledge succinct non-interactive arguments of knowledge. Sorry. So the question is, why do we need this? And of course there are many answers, and I would like to answer this by giving an example of a so-called zero knowledge proof of knowledge. And this is, you can prove knowledge without revealing the actual knowledge. So you prove it in a zero knowledge way. So just imagine a task where you have to convince everyone that you know a data set which hashes to a publicly known digest string. So we might call this knowledge of pre-image, right? So there's, on the internet, there's some hash value, and you claim that you have the data set that hashes to this value. Of course, the trivial solution would be to just publish the data set, and I can hash it, and if both hashes are equal, then everyone is convinced, and this can be seen as a proof, of course, but this is kind of naive, and sometimes publishing the data set might not be an option, really. For example, if the data set is a solution to a very, very famous problem, or so you just claim to have solved it and don't want to publish it yet. So a better solution would be to implement the hash function itself, not as a native executable, let's say on an x86 computer, but as a zkSNARK. And then if you implement it like this, then you get a proof of the actual computation. So in the end, you produce a hash value, but also a proof that you have executed the function. And you can have done this only if you know the actual data set. So if you implement a hash function, not native, but as a zkSNARK, then you kind of give a proof that you know a data set without revealing the actual data set. Yeah. Is this clear so far? Okay, so then the general roadmap is that we will start with our 3-bit cryptographic scheme, which we do all the computation in. The basic thing here is if we use just integer computation, we will just ramp up with crazy long and very not nice numbers. And so then I will introduce a toy example function, and then we go through the so-called Pinocchio pipeline, which is the pipeline for most pairing-based zkSNARK systems, somewhat. So we start with the so-called Algebraic Secret, and then from the Algebraic Secret we derive the quadratic arithmetic program, or QAP for short. Then we enter the setup phase where a trusted third party generates a so-called prover and verifier key. And then we do the actual worker phase where we execute our toy example function and produce the outcome and a proof. And in the last step, we do the verifier phase and verify that this proof is actually a valid proof. Okay, so yeah, usually the rules for talks are that you start somewhat easy and then ramp up to get more and more complicated to the end, so that people at least get the first 60% of the talk, but this is unfortunately not possible. So we have to start with the most complicated stuff, and that is that we have to introduce our cryptographic scheme somewhat. So the Pinocchio protocol and basically all pairing-based zkSNARK schemes require the following things. So they require a finite cyclic group. And for those non-mathematicians in the room, you can think about groups basically as the integers with addition. So you know from the integers that you can always add 2 integers to get another integer. You have one integer that's doing nothing in the addition, that is the 0. And for every integer, you have an inverse, it is the minus integer, so to speak. So just think about groups like this. And then we need a generator of that group. And a generator is one element so that you can create all the other elements just from this single element. For the integers, I think there's none of this, but you can think of this as a 1 because you can generate the 5 just by 1, just add 1 5 times to itself. But you cannot generate the negative numbers here. Yeah, and the most unknown part probably is the so-called pairing function, which is a bilinear map. We just need it in the last step, so it's not really important to keep this in mind right now. The basic property we need is this one, where you can just pull out these exponent out of the function, but this is just important later on. So in reality, of course, these systems are usually realized by cryptographically strong pairing-friendly elliptic curves. Yeah.
What's G sub T?
This is another group. It just says that a bilinear map takes two elements of the same group and then maps it to another group. So it doesn't have to be the same. It's just another symbol so that we can distinguish this from these groups. So, yeah, maybe like that.
So it's the target group?
Target.
Yeah, so you have two groups.
Right, good catch. But really, it just has to be a different group.
In the cyclic group, you define multiplication, not addition, but you mentioned just addition.
Yeah, I just want to have all those people who are non-mathematician to have an easy example in your heads. And you can, as an easy example, you can use integers with addition. But really, you cannot use integers with multiplication, because then you need fractions, and fractions are not integers. So multiplication is not a group.
And that example is not cyclic, right?
That example is not cyclic. But I will give a proper example here, which is our approximately 3.5-bit security system, which I came up with this group. So this is really everything. We don't have all the integers. We just have this number. So for example, 5 and 7 is not element of this. So just this number. And our group law is this. So we just multiply these numbers together like if they were integers, and then we take the modulus 23. And the modulus is you divide it like in school, like in junior school, or how you call it. You divide it by 23 and keep the remainder. I will do an example in a minute. Yeah, the generator we choose is 2, and I also will show that this really is a generator. That is, just by multiplying 2 with itself all the time, you get really all of these elements. Yeah, and then my non-trivial bilinear map, I defined this, and it actually works. So I'm cheating, because in actual cryptographic groups you cannot do this computation. It's considered to be invisible, but in our example you can do it. So, yeah. Okay, so to get a bit more familiar with the scheme, let's do some computation. Let's multiply 9 and 13. And so as you can see, 9 and 13 are really elements from here, right? So 9 is in and 13 is in, so...
Sorry, just a question. Can you go a step back? Can you explain why it's cyclic?
This group is cyclic because, let's say, you multiply 2 with itself all the time. Mm-hmm. Then you go through this here somewhat randomly, and then you start from the beginning and go through this randomly again. And so this is somewhat like on a clock. On a clock you have 12 numbers, so to speak, and you add them and you go around the clock all the time, right? Because 11 plus 3 would be 2, right? You go around the clock, and so this is cyclic somewhat.
But then how can you generate these numbers from 2?
Yeah, I will show this in a minute.
But you would need to do the modulo calculation.
Yeah, of course. Because normal multiplication, just forget about this. This is not happening here.
So you add the 2's together and then
you multiply the 2's together.
Sorry, multiply 2's together and you modulo 23 and then you get this number.
I will go through an example. So the example is here, so we multiply 9 and 13. And of course you would say, hey, this is 117, right? But it's not, because the multiplication is not defined as integer multiplication, but by this. So you first multiply them like...
And then taking the remainder group. Or
yeah, you will see it here. So first you multiply them if they were normal numbers, which is then 117. And then you divide it by 23 and take the modulus, and you see 117 is 5 times 23 plus 2. And so the remainder is 2, and then the result will be 2. Yeah, this is a bit tricky, but actually it's not that hard. You just have to get used to this.
Yeah, it's actually easy, but not simple.
It's not intuitive in the beginning, yeah.
Think of it as adding numbers on a clock.
Yeah, exactly.
That's
I mean, but it's okay. It's okay now.
So I will keep it here for a moment so that you can just look it up.
But 2 is the only generator.
No, I don't know actually. I haven't tested that, but it's a generator, so it's good enough. So, and then this is somewhat the cryptographic level because some computation are hard in this group, and then we also need the underlying finite field, and in our case, this is the so-called prime field F11, which contains these numbers, and then again, addition, and you can do addition and multiplication in this thing, but you have to do it modulo 11, so in this case. We will go through an example in a minute. So addition is normal integer addition modulo 11, and multiplication is also normal integer multiplication modulo 11.
Sorry, can you go?
Yeah, I was thinking that maybe an example
just
is...
a second, just give us some seconds to digest.
Yeah. I will go through an example, so that's probably better to just look at it.
Okay.
So the task here is now solve this equation for x. Right? I mean, we know if these were ordinary numbers, then we know how to do it, right? We would multiply this and then put things on the other side, blah, 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 and then we will get the result. And we can, because F11 is a field, we can actually do it exactly the same way. We just have to keep in mind that all the numbers we multiply have to be divided by 11 and then take the remainder. So the first thing I do is I multiply this with 5, so I somewhat resolve the brackets. So, and then I get to this point, right? And now 3 times 5 is 15. No, it's not 15. 3 times 5 is 4, because 15 divided by 11 gives the remainder of 4. And 4 times 5 is actually 9, so we arrive at this point. As I said, this is the hardest part. We just have to get used to this somewhat. I also have multiplication and addition tables here, so you can really, you don't have to compute it, but you can really just look it up if you want.
Is that the group?
No, this is the finite field because we use this much more. The group will only be used in the end. Right?
Did we pick the field? Was it somehow fixed by
Yeah,
the
it was fixed by the group, and I will explain this in the next slide. So now what would we do if these were ordinary numbers? We put this on this side and this on this side, right? And so we arrive here. But now the catch is that in the prime field F11 there is no minus 3, so to speak, and there is no minus 9, so we must understand what minus actually means. And the negative of a number is that number that you have to add to the original number such that you get 0. So in this prime field, really it means to get that number that adds to the original number such that you get 11.
So is there a difference between 4 times x and 3x?
No, I just forgot the dot.
it's
Yeah, it's the same thing. Yes, it's a blend of me. So then, then the negative of 3 is of course 8, because 3 plus 8 equals 11, and 11 modulo 11 is 0. So the negative of 3 in our prime field is really 8. And the negative of 9 is really 2, because 2 plus 9 equals 11 or 0, so to speak. Yeah, and then just I excluded x here, and then 4 plus 8 is of course 1. And so the solution to this equation would be 2. Right? And so whenever I do computation in the following, I do them this way. So if you think, this computation is wrong because it's the wrong number, it's probably not, because I have done it 100 times. And so, and so this is the relation. This proves that 2 is a generator, actually, and it also proves why F11 is our base field, because we can put 11 numbers here in the exponent, and then we get a repetition here. So this is also cyclic, right? Because 2 to the power of 0 is the same as 2 to the power of 11. Yeah. And this is something we cannot do in actual cryptographic groups, because it's generally believed that finding the discrete logarithms is hard. But we can just derive it from here. We just take this and take the logarithm on both sides. So this is we don't need it right now. We only need it later for the pairing. So. Yeah, and this is how I think about these things as 2 levels. You have the base field at the bottom, and then you have the group at the top, and you can go from bottom to the top by exponentiation with a generator, and you can get kind of from top to the bottom by logarithm. Yeah, I mean, I already explained this somewhat. Why not use ordinary numbers? And the answer is that in groups like G, certain computation are much harder, even for computers, and for example, it's generally believed that this equation cannot be solved easily for x. Right? Yeah. Okay, that's it. That's basically the cryptographic scheme. And now we have to come up with some kind of computer program, which we will snarkify. And yeah, I take the most easy one that is expressible in this scheme. And so now our computer program takes 3 elements from our base field and just multiplies them together. This is as easy as it gets. I mean, the thing is, of course, you can do a more complicated computation, but it's not feasible here because everything is so complicated. We will see it in a minute. Okay, so now that we have defined the function, we go through the snarkification process through the Pinocchio pipeline, and this starts with the so-called algebraic secret representation. Every finite computer program, every bounded computer program can be represented as an algebraic secret. And algebraic secret are really nothing but directed acyclic graphs that represent computation. So you can think of a graph, but the graph has errors, so it has a direction and no cycles are in the graph. And then vertices with only outgoing edges, which we might call leaves or sources, represent the input values to the computation, and vertices with only ingoing edges, which we might call roots or sinks, represent the output of the computation. And the internal vertices represent field operation, and we only have 2 of them. We have addition and multiplication. And the basic idea here is that you can execute a circuit. So you put the input values to all the leaves and then follow the edges through the graph. And then whatever the vertex is decorated with, addition or multiplication, you do that. And then you follow the graph until at some point you enter the roots of the things. And the basic point is that usually in reality you don't have to come up with a sequence yourself. This is most like if we program a normal computer program, we don't write assembly code, right? We write higher level code and it compiles down to assembly code, and in Snark it compiles down to algebraic secret, really. Yeah. Something I want to note is that different compilers give very different secrets. Secret representation and compiler optimization is important because secrets are not really made for computer chips. So the execution of a secret in reality is really slow. And when you have large secrets, that's considerably slows your computation. And to just give a reminder, this is not an actual Snark secret, it's just some picture I took from the internet to remind people that this can be very complicated, right? Actual secrets look a bit like this. So, yeah. But not ours. For our function, the secret is pretty straightforward, and we can just represent it like this. But it's not the only representation. We can represent it differently or arbitrarily complicated, but this is one possible representation. So we put the input values x1, 2, 3 here, and then do the computation. So whatever we put here, we multiply it with what we put here to get this, and then we multiply this with what we put here, and then we get the final output, right? So this DAG happens to be a binary tree, but this is just because of our example. This is not how it looks in general. Okay, so the point here is that we have 2 multiplication gates. And the most important part is, for what follows, is that every edge gets a label, and the set of all the labels is really important here. And we have somewhat distinguishable labels. So we have labels that are related to input and output, and labels that are related to middle terms in the computation.
Is it also arbitrary that these are multiplications? One could be addition, it's just for this example.
Yeah, one could use addition, but addition is somewhat handled differently in zkSNARKS. Actually, they say addition comes for free because addition does not add to the complexity of the system. And if I would have used one addition gate here, then things wouldn't work out. So I really was forced. This is the basic example. It doesn't get simpler than this one. We have to use at least 2 multiplication gates for this to work. So the next step is what are assignments. And an assignment in general just associates field element to all edges in an algebraic secret. You know, the edges were labeled, so we represent every label with a number, so to speak. And the major point here is that an assignment is valid if the field element really arises from executing the secret, and all other assignments are called invalid. And the first major offshot here is that valid assignments are proofs for proper secret execution. That is, maybe we just go through our example. And as we can see here, this is a valid assignment because we have the input values 2, 3, and 4, which we just put in here, here, and here, let's say. And then we multiply 2 and 3, and this is 6. So this is valid, right? And we multiply 6 and 4, and this is, of course, 2, because 6 times 4 is 24 real numbers, and the remainder is 2. So this is a valid assignment. All these numbers here check up if you really execute the circuit. To give a counterexample, a non-valid assignment here would be to have the same input values, but then here appears 7 and here appears 8, and this cannot happen if you execute the circuit, right? Because 2 times 3 is not 7, and this is not 8. So we have valid assignment and invalid assignment.
Question. The general case is that in a circuit there are more than one valid assignment. Is that correct?
Yeah, of course. For every input set, you have a different valid assignment. You can choose different input sets here.
Now, even with the exact.
I think that would depend on the actual circuit. In this circuit, not, because if this number is determinated and this number is determined, this number there's only one possible choice here.
Maybe for this example.
Yeah, there might be other examples. I don't know. That might happen. Yeah.
And there are cases that it's also doing the finite field arithmetic, yeah?
Hmm?
It's doing the finite field arithmetic there too.
Yeah, because.
And that's when the security comes in. When you want
No, there's no security in here really right now, because this is done in the finite field, and it's generally believed that in the finite field all computation are somewhat easy. After that we go to the group, and there things becomes more harder. And yeah, this 2 just appears because we do the computation in F11. 6 times 4 is not 2 with ordinary numbers.
Question.
Yeah.
This valid assignment seems to, the order matters here, right? Like permutations of that valid assignment are still.
It shouldn't. It really shouldn't.
You have to declare what is what is in one, what is in.
Yeah, I have. This is our circuit. Where is it? This is our circuit. So I have defined what are these. This is our assignment. In one always means this edge, nothing else.
So a question on the live stream is this generalized to any computation in a Turing machine?
In a Turing machine? Is this generalizable to any computation in a Turing machine? I don't think so. I think this is not Turing complete. I'm not the expert here, but I think the general rule is that you can only represent bounded computation. So you don't represent infinite loops, because then you would have infinite graphs. So a bounded computation is a computation that terminates. So not an infinite loop, right? Because you have to unroll the computation and then transform it into secret. But
It would make sense to prove beforehand that you don't have a whole problem if you want to execute it in a zero knowledge. Right?
yeah, I think you don't have to go that far. You just have to prove that your computation is bounded somewhat. But this is not so much my expertise. So the offshot here is really that valid assignments are proof for proper secret execution, because if you have the valid assignment, then you must have done, or at least someone somewhere must have done all the computation at least a single time. Of course, if someone does it a single time, you can just share it and then everybody can run with it. So this is not really a proof for proper execution, but it's a major step forward.
But isn't sharing a valid assignment the same as sharing that you all
Yeah,
your input?
probably. I don't know. Yeah, so, but these proofs are not short. If I send you a valid assignment and you have to verify the proof, you have to do all the computation yourself again. And then you say, oh, this is a valid assignment, but I have done the computation, so I could have done it in the first place. Really no point. This is not a short proof or something. And so the major step now to get short proofs is to transform a circuit into a so-called quadratic arithmetic program. And the quadratic arithmetic program of a circuit is really nothing but a set of polynomials, really. So, and you can think of them as building blocks to encode circuits into a polynomial t and assignments to circuits into a polynomial p. And the first major point is that the polynomial p you get from assignment is divisible by the polynomial t if and only if the assignment is valid. That is, if you have a valid assignment, then this equation holds. That is, there's another polynomial h such that this equation holds. And if the assignment is not valid, if you just made it up, then the polynomial you derive p doesn't hold this equation. But still, this equation is really complicated because you have to think of these polynomials as really huge. Like they have millions of constant or something. So these are huge polynomials. So if you divide p by t, this is also a very complicated computation. So it's still not short.
Sorry, is t fixed? Did we fix
Yeah, t will be fixed later on. When we compute the QAP, then t is a system
So
constant.
it's part of the circuit.
It's part of the yeah. You can derive it for the circuit, and it's a constant then.
Can you say again why we're doing this step?
Because we have the circuit, and the circuit is enough to prove that you have done the computation, but it's not a short proof. If I get a valid assignment from you, and I want to verify that this is a valid assignment, I have to recompute the whole circuit. And so I have to do the same amount of work. It's not a short proof, and the whole point of SNARKs is to get short proofs.
And then would T be fixed? Would it be fixed for individual people so that I can send the validation to someone, or is it like just for that one?
No, T is fixed for the circuit. But you can later on generate different proofs for different people.
Okay.
The different proof keys, I mean, for different people.
Okay. And where do the polynomials come in? Why they are polynomials?
Yeah, this is the next step I will come. So still, as I said, this computation is really hard. But the second major point, and even the whole idea here, is that with overwhelmingly high probability, this equation can be verified in a single point. So instead of really doing the polynomial equation, you can just do this, and these are field elements. So this is really short. So you go from something really, really big to something really, really short.
This is only one test, or are you doing actually multiple tests to ensure that it's not like
This is just one test. And for polynomials, this is good enough, because two polynomials can only share a finite amount of points. They never share an infinite amount of points or something. So, of course, you lose some degree of confidentiality, but it's still very, very high, the probability. But on the other hand, you have to make sure that the point S is not known. So you have to have someone which come up with this point S and then later deletes it. So we need a trusted third party for this. Yeah, so
Do you just check for 1 point, or do you check for like 100 points?
no, you just check for 1 point, because there's really, probability speaking, not much of a difference if you check for 1 point or for 10 trillion points or something.
Is it also the same that the point is fixed for the circuit, or it depends on
The point will later be chosen by the trusted third party as a secret, and then they set up some stuff so that other people don't have to know the point, and then they hopefully delete the point, so no one knows the point anymore. This is why we have to have a trusted third party, unfortunately, for this protocol. But really, you can imagine how much of a step it is from this huge computation to this very small computation. So it's maybe in some system it's where it's a trusted third party. So how do we compute the QAP then? And now the QAP is a set of polynomials, a fixed polynomial t, and then these polynomials v, w, and y. And okay, so to derive the QAPs, what we first do is for every multiplication gate in the circuit, we choose randomly one element from the base field.
This is what I don't get. Why is it a random element?
Why is it random, or why is it
Yeah,
an
why is
element
it
at all?
random? Why is it random? Why are we calling M1 random, let's say 2, and M2, let's say 11
Why not?
or 10? What's the reason?
There's no reason. We just need a bunch of elements. You don't have to compute them randomly, I think. It's not really the point.
Doesn't really matter.
I think it, I wouldn't hold my head for this, but I think it doesn't matter.
So is it safe to say choose arbitrary elements?
Yeah, choose arbitrary elements. Okay, because you don't want cryptographic randomness. Okay, then arbitrary would even be better, yeah.
And K, is this K determined by something?
Yeah, this is the number of multiplication gates in your circuit. Addition gate don't count here. They come in for free SSA, but for every multiplication gate, so you have a big circuit, you have a million multiplication gates, and you have to come up with a million random or arbitrary elements.
But they have to be distinct M1 and 2.
This is also a question I don't know. And even the question is, do they have to be invertible? Can I choose 0 all the time? I don't know. It's not specified in the paper, and it would be interesting to do more research on that. So once we have chosen them, then the target polynomial t is really computable pretty easily. So it's just the multiplication of the zeros of a polynomial, so to speak, which has the zeros of the set. Yeah, so in our case, we have to choose two elements, and then we build t like this, but we will come to this in the example in a bit. Yeah, and this is somewhat non-intuitive, but it's not hard. I will just go through it, and then we will do with the example, and then you get the point. But this is really not, or I wasn't able to explain it really simple. So the polynomials v really represent left inputs to multiplication gates, and the polynomials w represent right inputs to multiplication gates, and the polynomials y represent outputs of multiplication gates, so to speak, right? So our polynomials from v, or a polynomial from v indexed by the edges, is 1 at a multiplication gate if the edge is a left input to that multiplication gate and 0 otherwise. And similar, the polynomials from w is 1 at a certain multiplication gate if that edge, that index, that polynomial is a right input to the multiplication gate and 0 otherwise. And the polynomials from y is 1 at the multiplication gate if that edge is an output of that multiplication gate and 0 otherwise. Yeah, it's just crazy to explain. Now I will do it in a second. And then the offshot here is that from this polynomials or from the QAP and a valid assignment, so if you have a valid assignment, you can generate this polynomial. Okay, and let's go through our example to make this more clear. So as you can see in our circuit, we have two multiplication gates, right? And so we have to choose two numbers, and as it so happened, I choose 5 and 7 for this, which are in our prime field, right? I cannot choose 13 or something, but 5 and 7. So then the target polynomial is really easy. It's just this equation, and I insert 5 and 7 here. Yeah, so what's minus 5 in F11? 6, yeah. And minus 7? Yeah, right, good. Great. So, and then I multiply this, and this is then our target polynomial. And so we have to come up with these polynomials. And okay, so we have to apply the Pinocchio rule. And really, we go through all the edges here, right? They are indexed by all the edges. And the rule is that if the appropriate edge, let's say in 1 in this example, is a left input to a multiplication gate, then the value has to be 1 at the chosen number. So because this edge is a left multiplication gate to M1, the polynomial at the number we have chosen for M1 has to be P1. And because it's not a left input to this multiplication gate, right, it's just here, the value has to be 0. And so in 1 here is not a left input to any multiplication gate, right? It's the right input to this multiplication gate. So on both multiplication gates, the polynomial is defined to be 0. These are not the polynomials yet. These are just equations from which we can derive the polynomials. And the same goes for in 3. So in 3 is not a left, obviously not a left input to any multiplication gate. So both of them have to be 0. But now mid is a left input to the multiplication gate M2, but not to M1, so this is the defining equation for this polynomial. And then last but not least, the output, of course, is not a left input to any of the multiplication gates. So that's the rule, really. And the same goes for the right inputs. So, of course, this is not a right input to any multiplication gate, while this is the right input to M1, and this is the right input to M2. This is not a right input, and this is also not a right input, so I think this is somewhat clear, right? And the same goes for the y. So the rule here is that it has to be an output, and of course these are inputs, so none of them is an output. All of this is 0. This is an output from M1, but not an output from M2, and this is an output from M2 and not from M1. So this is how these numbers came up. Yeah. So these are not polynomials, obviously. These are equations. But we know from mathematics that a polynomial is defined on certain points completely. So if you have a polynomial of degree n and you have n plus 1 points, then it's completely defined on this. And so we have 2 points, right? We know that whatever this polynomial looks, at the point 5 it has to be 0, and at the point 7 it has to be 0 too. So what we really do, we have specified our polynomials on 5 and 7. and the only polynomials that are determinated on 2 values are really linear polynomials, so linear function really. In reality, of course, these polynomials are much more complicated, but yeah, our example is a simple one, so we have linear
The
functions.
degree of the polynomials will be 1 minus the number of multiplication gates.
Exactly, yeah. Right.
The number of multiplication is minus 1.
Yeah. That.
Yeah. So, of course, I don't compute all of them right here in front of you. So just go through the example of the in1 polynomial. So it is a linear function, and it's determinated on two values here. So we just plug in this value here and this value here, which is this, right? Because it's a left input to this, but not a left input to this, as I said. And now these are 2 equations with 2 indeterminates, so we can use basic Gauss algorithm or whatever to come up with a solution, and the solution in this case is 5 and 9, and so our input polynomial here is f is 5x plus 9.
You can probably use like FFT or something to.
Yeah, you can. I don't know. I mean, I think most people just use Lagrange interpolation to do this. But as I said, this is computationally expensive, and I think this is one of the hardest part in the overall generation of the setup phase. Would be great to have something that will speed it up, but at least it's a one-time job, right? You just do it for once, and then you can use the computation over and over again. Yeah. So I did the computation, and this is, these are the polynomials that showed up here. So really, if you go through this at home or something, you can see that this really reflects left input to C or whatever, and this reflects the right version and the output version. And then our QAP is just this set. So it's a target polynomial, and it's a set of left inputs, a set of right inputs, and a set of outputs. And so, yeah, what's really the point of this? The point is that we want a polynomial p that is divisible by this polynomial if and only if the assignment to the circuit is a valid assignment, right? And you can build it like this. And I cannot go through all the details of the proof that this is really divisible by t if and only if it's a valid assignment. But the intuition is that these really represent left inputs, and these represent right inputs, and these represent outputs. So if one is a left input and the other is a right input, and you multiply them because it's a multiplication gate, and what you get is the output, then this is 0. Right? And so the polynomials have to be defined in a way such that this is separated for all the multiplication gates, so to speak. So the polynomials are only one at one of the multiplication gates. Okay, so let's do our valid example. I think I have it here. Remember, this was our valid example. And then we plug in everything here. We plug in the polynomials from the table, which unfortunately I cannot show right now, and the coefficients here from the valid example. And then we get this monster and just compute it down, blah, 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 until we appear here. And so, as it so happened in this case, the polynomial is really the same as t. This is an accident, and really I was just too bored to do the computation again with other numbers, so I just kept with it. This is of course divisible by t because it's equal to t, and so it's of course divisible. If we do the same thing with a non-valid example like this, as you know, here cannot be a 5 if we have the same input values, and here cannot be a 9, then we come up with this and do the computation, blah, 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 and this is our polynomial. And when we do polynomial division to check this, we So, yeah. Yeah, it's just, so it's not divisible by t because there's a reminder, and so it's a, Okay, so this is really the point, right? So if you were a worker that had the circuit and that executes the circuit, then you are able to come up with a polynomial that is divisible by t.
Remind me, what was t again? It was the
T is a target polynomial. In our case, it is this one.
Okay.
Yeah.
So is the reason addition gates are free because they don't affect the degree of the polynomials?
That's a good question. I mean, the way P is set up is that you just P is just multiplication of everything that comes from the left and everything that comes from the right, just multiplication, not addition. So I think that is why addition comes for free, but really I can't say in detail.
Is it called quadratic arithmetic program?
Because the polynomial is not quadratic, right? But it's so to speak, you have multiplication, so you quadrate polynomials, so to speak. I think that's the reason.
If I would have a gate with 3 inputs, it would not be quadratic.
No, multiplication gates cannot have 3 inputs. Addition gates can have, and even in the Pinocchio paper, there are some addition gates developed which has more than 2 inputs. Yeah. Let's keep it, because I'm not very qualified to explain the details of this. Okay, so the next step is that we need a trusted setup phrase set. So we need some party that we.
Can you bring up what the Pinocchio rules were? So what you used to get the W and Y?
Yeah. So basically, the Pinocchio rules say that the V's are left inputs to multiplication gate, to a certain multiplication gate. This one, right? Yeah, is that clear? Okay, that's the point. Okay, so the QRP is a cryptographic scheme, and the secret is now public knowledge. It's just somewhere on the internet, and now we need a trusted third party, and this trusted third party has to come up with a bunch of random elements from the base field. So of course the same question goes here, right? I think these values have to be somewhat random, because you should not be able to deduce them in whatever reason, because they are really later called the toxic waste. And then the trusted third party comes up with the so-called prover key, which the prover needs to generate the proof, and with the verifier key, which the verifier then later needs to verify the proof. Yeah. And this party has to be trusted third party, because we have to trust them that these values are deleted later on, because this, for example, is the secret point where the polynomial is evaluated on. And so, yeah, we have to trust this party that the elements are deleted. And as most of us know, Zcash went through this whole ceremony to somewhat do this. Okay, and then the prover key looks like this. We have our generator, right, and then we have this. So it's really a set of group elements used to encrypt the non-IO related part of the polynomial P. And as you can see, these are just indexed by the midterms. So in our example, these would be the input and output related elements, and we just have one middle related edge, so to speak. So in our example, this will be really easy. But for every edge that you have in the middle of the computation that is not related to input and output, you put one of these elements into the prover key. So the prover key really depends linear on the number of internal edges. And this can be seen as a drawback of the system, because prover keys can become really large. Like in the Pinocchio paper, there are example circles where the prover key has gigabytes, like 5 or so gigabytes of size. So because when you have 1 million of internal vertices, then you have 7 times 1 million of these elements here, right? So these elements really later will check the polynomial P, and these are additional security constraints. I will not go through this because some of this has to be, was optimized away already in the Groth paper. So we will just leave this like this. And of course, the prover key is not unique. As you asked previously, you can generate different prover key because you cannot come up with a different set of toxic waste elements. And the verifier key is somewhat the completion of this. These are, here's a target polynomial encoded, evaluated at the secret point. And this really encodes the input and output values of the circuit. And the same goes here. So it also rises linear in the number of input-output gates. So if you have a computation that had a lot of input and output gates, then the verifier key would be large.
Can you gain any intuition from the way these are arranged on the page?
No,
Okay.
really, yeah. This part I skip completely because it's already solved somewhat in the Groth paper. That's not unique. So in our yeah, these are the random numbers that you have to choose. They are parts of the toxic waste. Yeah, so in our example, we just choose this random number, so we just go 9, 8, 7, 6, 5, 4, 3, 2, and then we compute this additional number here. Right? I mean, we have not much choice. We just have 11 elements in our base field.
R sub y the multiplication of those two?
Hmm?
R sub y is the multiplication of R sub b times R sub b?
Yeah, this is the multiplication in F11.
Ah, okay.
Yeah. So now we encrypt these elements. So we have chosen these elements, and now we encrypt them by putting them in the exponent of our generator. So now we get group elements, really, right? So, yeah, how do we do this? I mean, in our example, we can just look it up here. These are the generator rules, and then you can just skip through this and do the computation. You can do it by hand. That's maybe overshot. Just 2 to the power of 9 equals 6, and the others are similar. So in our case, the prover key, because we only have a single middle edge, so to speak. We only have a single middle edge, so our prover key will look like particularly simple. And so we really look up our quadratic arithmetic polynomial and then look up the v-mid part and insert our secret evaluation point 7 into this, and then we get this.
7 is 1 in this case.
Yes, 7 is the secret value choose from the toxic waste, so it's part of the toxic waste. And this is the point where we evaluate all the polynomials at. So instead of using the actual polynomial, we use the polynomial evaluated at 7 in all our examples.
Because we choose for M1, 7, right?
No, we choose 7 as part of the toxic waste. So here, this 7 really is this 7. It's also for M2, right? You're right, but this just happened. So it's just happened. Because we only have 11 elements, so it will happen. Yeah. So we insert the polynomials, and then it's just a matter of computation, blah, blah, blah. And at the end, we will derive our prover key, which in our case is this. So it's just a set of group elements, really. Right? So as I said, if we had more middle edges, like millions or so, then each of these will not contain just a single element, but each of them will contain a million, or whatever this is. So this grows very fast. And the verifier key, the definition is this one, because we have now, for the prover key, we had just one edge, but now we have more edges. We have 3 input edges, so and 1 output edge, so this adds considerably. This one, just forget it. I just not deleted it, so this is it's not there. Yeah, and then again, we look up these polynomials in the QAP and do some computation, and then we derive at our verifier key here, really. So if you want to know how this is done, then probably should do it at home as an exercise, because this is just this is just too much now just for the talk. Okay. Of course, the verifier key is related to the prover key, right? If you would choose a different kind of toxic waste, then you would generate a different prover key and also a different verifier key. So prover key and verifier key really comes in pairs, and these pairs are often called common reference string. And so in our example, this would be the common reference string of our QAP and of the secret CF. Right? Because we could have choose other secrets for our function and other QAPs. So
Is common reference string synonymous with structured reference string? Is another thing?
Yeah, to distinguish it from random reference, for common random string or something. Yeah, so that's the setup phase. So this is done now. What's now out there in the public is the actual problem, the circuits, the QAP, and the common reference string. So this is just out there, and someone now might take these things to do a computation. So, and the task then is, given an input set in, execute the circuit to compute all the intermediate values. This is important, and also the output value. Of course, in ordinary computation, you are just interested in the output value, but really, when you want to prove proper execution, you need all of this. Yeah. So proof generation works like if you have done the computation, then in the end you get a valid assignment, and you can use the valid assignment and the QAP to compute the polynomial P. And the first step, what you do is you divide P by T, and then you get this polynomial H. And because the assignment is valid, this division works, so to speak. And then you use the prover key, which is public knowledge, to compute this proof. And this proof is really, really amazing. What you do here is you sum up all the parts that are related to the middle stuff of the computation into one element. So no matter how many steps there are in the middle computation, 1 or 1,000,000, everything just sums up to one element. And so the proof really has constant size. So this is great. In the actual Pinocchio paper, the proof has 288 bytes, no matter how large the computation is. I mean, the offshot is you have large prover keys and large verifier keys, but the proof actually is a constant one. So you basically only have 8 elements of the group. Because everything that happens in the middle, you just compress it by linear combination, evaluate it at a certain point, and put it into the group, and that's your proof. So yeah, you can say that Pinocchio really has short proofs.
Is that already the zero knowledge part?
No, he has no zero knowledge so far. This is additional things you have to check to make this a valid proof. But as I said, we will not go through this because Gross already simplified this down to three things, not 8. It's also yeah. So one thing to remember here, that this might look easy, but it's actually not, because the prover doesn't know the secret element here. So even if he can compute this, and he cannot compute the evaluation at the point S because he doesn't know S as a secret. So the question now is, how do we actually generate the proof without knowing the secret value? And
knowledge of exponents or something?
I think that goes into this, yeah. What he's doing is he basically used the exponential laws, right? So multiplication in the group is translated into addition into the exponent, and multiplication in the exponent is done to exponentiation in the group. And so, for example, if the prover wants to compute this, and he only knows this from his own computation, what he can do is he can compute this. Because this element here, just this one in the bracket, this is part of the prover key. And this comes from the actual computation, and then you just have to multiply these things. So you don't have to know the secret value. All you need is the prover key, really. And all these elements are in the prover key. And if the prover key is very large, this gets compressed because you just multiply it down all the time. Yeah, so in our example, again, we unfortunately, I don't have the prover key here, I think. Yeah, so you gotta take my word for this somewhat. So the middle index from the proper execution was 2 times 3, remember, so this becomes 6, and now we just have to put this into the exponent here. All these numbers here are part of the prover key already. So we just have to take these elements from the prover key and then exponentiate them to 6, and we can use our lookup table. And so we generate this proof for our computation. So giving input value 2, 3, and 4 and output value 2, this is a proper proof that we really have multiplied 3 numbers to get our result. Oh. Yeah. So this is it. Now the prover generates the proof and he publishes the proof. And the Pinocchio protocol is a so-called public verifiable protocol. So everyone can check the proof now. And this is called then proof verification. So the task is that given an input set E in and an output set E out and a proof P, verify that the proof is correct. So, and then remember that the whole point was that if the prover has executed the computation, then he knows a polynomial P that is divisible by T, right? And we don't have to check this, but we can evaluate this on a certain point. And for us also it's important that P is not just some P, but it's a P that is alleged from those input and output values. And we can check this really by doing this computation. And remember that B is the pairing function. Yeah, we will go through the example now. And this is something the verifier can compute, because these are the polynomials related to the input and output values. And this is coming from the proof. So this is what the prover has done. And the same here. So this can be computed by the verifier, and this comes from the prover. And this is part of the verifying key. And this, the prover knows this polynomial h, which is the divisor of p and t. So this comes from the prover. And again, this can be computed by the verifier, and this comes from the prover. So the verifier shouldn't have everything in here now. And also, the Pinocchio protocol especially needs to do this computation. We won't do this, as I said. This is optimized by the Groth paper. The problem here is that this pairing function is usually very slow on cryptographic curves. So if you want a fast system, then it might be advantageous to drop this to as little elements as possible.
That was a symmetric pairing function.
Yeah, you can also use antisymmetric pairing functions. So I think there's a proof that you cannot reduce it to just one pairing. And the Groth paper, I think, reduced it to 3 pairings, so it's still an open question if you can reduce it to 2 pairings. But yeah. So let's see, why does this prove that P is divisible by T? And this is somewhat the most complicated part of the talk, so let's just try to get this. So as I said, the task is to verify that P equals T times H for some polynomial H. And we can have a succinct version of this, so we can do this at a certain point only, right? And also, if this is a group generator, then we can do it encrypted, so to speak, in the group. So the task really is to check this. And the point is here that I want to show that this really is just this, and this is what the prover is doing.
Verifier.
That the verifier is doing, right? Okay, so how do we do this? So we want to prove this, right? And so we just define this as this, and then we go from here to here, right? We just insert this into K, and then we get this one. So now we use the properties of the pairing function. That is, we can just take this and this out of the exponent, and we do this on both sides, and then we come to this step. And of course you can say, hey, wait a minute, this is not known, this is forgotten, and so we cannot compute this. And this is true, but this is just a principal mathematical explanation why these two things are the same. So we don't really need to know them. Okay, so now we replace the definition of P of S by the actual definition of P here, which is the left input part times the right input part minus the output part. And this equals then this again. And so we do some group magic, because this is a minus. This really means that it's the inverse of something. So we can multiply with the inverse and put this part onto the other side. Yeah, and then we can just use the properties of the pairing and put this into the first one, this into the second one. And so we arrive at this one here. And this already looks like something like our proof. So we use exponential laws and take this one out, and this is our equation. So what the verifier, when the verifier really computes this, what he's really doing is he's checking this equation. So yeah, and that's, I think it's the whole point of the zkSNARKS protocol. Yeah. So as last but not least, let's go through this in our example. And really, unfortunately, I cannot show it. So I really just put everything, plug everything in that we have so far here, and we get this. So 1 times 12, this is the neutral element, so this doesn't really change, and we plug this in here, and then remember the definition of our pairing function, which is this one. And now we can look up the base 2 logarithm, hopefully, somewhere. But anyway, so if you would have looked this up, then this would be like this. And then you multiply it in the exponent, and in the end you really get 2 equals 2 in our scheme. So this means that the verifier has verified that the proof is an actual proof.
Would it be safe to say that the key result from this growth paper is that you can verify these proofs with this bilinear pairing?
I think this is also a shot of this paper, because you use the binary pairing to verify proofs. But I think, as far as I understand, the gross paper optimizes this. Because here you have 6 or somewhat pairings, and in the gross paper you only have 3. So the gross paper makes it a little more efficient.
So is the main degree of freedom in designing pairing-based snarks this encoding, like the QAP stuff is kind of...
I think the QAP and everything that follows from the QAP is somewhat automatic. Yeah. Really, the optimization part comes from deriving the circuit from the original program. Okay, so then last but not least, maybe let's have a word on zero knowledge. So in our computation, we had 3 input values, and we just proved that when we multiply these 3 input values, we get the proper output value. But at some point, a prover might not want to publish his input values. So what can he do? And the point here is really that we have to extend the verifier key by this. This is not so important for now. The really important thing is that we expand the polynomial p by some random numbers like this. So the worker generates 3 random numbers and then adds this and this and this to the polynomial p. And now the worker is free to choose where to put this randomness. So in our example, let's assume that the prover wants to hide this first input value. So the worker really says that, hey, I know one number that multiplies with 3 and 4 such that the result is 2, but I don't reveal that number. So what he can do is, because this is the left input, he can take this randomness and just add it to the appropriate value here, because C in 1 is the number he wants to hide. So he can put this to the C in 1. Yeah. And so now this is not the actual number anymore, but it's the actual number plus some randomness, and so the number is crumbled. You cannot reveal the number anymore.
So it's just simply blinding the input value?
Yeah, you blind the input value by adding it to a random other number. Now let's suppose he wants to blind this number and this number, let's say. So he wants to blind two parts of the right input. So he can split this into 2 and then add half of this to the first and half of this to the second. And you can really do this with an arbitrary amount of numbers. So you can really choose which numbers you want to hide, and you can even do it with the output. At some degree, this becomes trivial, because at some point you can say, hey, I know some bunch of numbers, do some stuff and will give some output, so everything is zero knowledge. But really, in our computation, for example, if you want to hide all 3 numbers, then what does it really mean? It means that I know 3 numbers that multiply to 2, but I don't reveal which numbers these are.
And if you were to blind the output as well?
Yeah, then you have zero knowledge of zero knowledge. I don't know. Then you know how to do stuff, but
something, right?
Yeah, you're proving the computation. Yeah.
Yeah, but you can also somewhat randomize the proof itself, because you can put some of this randomization into the middle part, and then you have generated random proofs. So every proof is different from a previous proof.
Do these polynomials would it be safe to say that the degree of obfuscation you want is in correspondence with the degree of the polynomial that you pick?
I think the degree of obfuscation is perfect. It's zero knowledge. You cannot have more obfuscation. You can have as much obfuscation as you want, because you can divide this randomness into arbitrary amounts of randomness.
So it doesn't matter if you choose these R's to be really high degree. They could just be a scalar multiple of T.
Yeah, but they should be random, right?
Okay.
Yeah.
They're elements, they're not
And to be clear, you said spread. You mean just take the same randomness?
Yeah, because here you just have one randomness, right?
Yeah.
And in principle, you can just add it to one of these. But if you want to add it to two of them, then you have to split it in part. But randomness split it by half is also randomness, so you can split it an arbitrary amount of times. Yeah, and that's it.
Cool. But when you say split the randomness in half, so imagine you have 32 bits of randomness and you split it in half.
Yeah, that's a good question. I don't know.
So you'd have to generate.
Probably.
Okay, I see.
You can always generate more.
Yeah.
Yeah, I think so.
Just generate some. Apply just.
Yeah, I don't know.
Call you in. Just use it. Okay.
So one thing I want to say, because in the beginning I started with the example that if you snarkify a hash function, let's say SHA-2, then what you get in the end is some way to prove that you have a preimage of a hash function without revealing the preimage. So this is how you do it, right? So you will just scumble the preimage and then publish this, but it's not an actual preimage, but still you have a proof that this, if it were the actual preimage, not snarkified or not zero knowledgeified.
And in that case, you probably also want to blind the intermediary gates.
Yeah, this is, definitely. But this is, you can do this easily.
And somebody did it earlier. I was thinking about this. They asked if it was Turing complete, and I believe it is Turing complete as long as, like you said, it's bounded.
Yeah, then it's Turing, but that's not Turing complete. I think that the official term is alpha Turing complete or something, lambda Turing complete or something like that.
Step limit,
because you cannot encode infinite loops. That's the only thing that you cannot encode.
Okay. I didn't know the term for that. What did you say it was?
This is in the Simplicity paper, which is a great new language for smart contracts. You should look it up. And in that paper, this is explained. Because Simplicity is not Turing, but almost Turing complete language.
Blockstream.
Blockstream, Turing. Yeah. Okay, yeah, that's it. So.
One question. Why is it that in these protocols, zkSNARK, especially the Snark protocol with the transparent setup, you always have to check for low degreeness?
I don't know. This is not really this.
Is it?
I don't know.
Divisibility by the team polynomial that it's automatically?
I can only give a trivial answer because a degree doesn't appear here at all, right? So shouldn't matter.
I think the Snark constructions turn the question of checking for divisibility into a question of checking for validity.
That was my feeling as well, but I just...
Stark is not SNARKS, right? It's a completely different approach. Yeah, that's it.
I thought I heard you mention something about recursive snarks at the beginning.
Yeah, this I cannot say much about this. I hope that if this works well and people like this talk, then we can go through additional steps. The next step maybe will be the bulletproof protocol, and it goes through steps to arrive at the Halo protocol in the end, and then have a good talk about recursive
There are
snarks.
two now, right? There's Halo and there's Fractal, which he has a...